We're now ready to start chapter 14. We are moving from talking about multiple outputs to multiple inputs. So in the chapter 13 applications and everything we did in chapter 13, we had vector outputs, which meant our functions were like r of t, which had x of t, y of t, z of t. Okay, single in, multiple out. And other than a few kind of special cases where we talked about velocities and we talked about arc length, really it was just an extension of Cal 1 in the sense that to take the derivative or the integral, all you have to do is apply it each individually. Okay? Now we consider multiple inputs. Now to make our lives fairly simple, we're going to just kind of flip it over and have single outputs and multiple inputs. Okay? We're going to do what are called real valued functions of several variables. Okay? So that's hence the name of this particular section, and then we'll start talking about how we take derivatives. Single output, but multiple inputs. And that changes things fairly significantly because we're not, well, I mean, it's not that difficult, but it does create a lot of issues that we need to work through. So to begin with, let's just start talking about what we mean by a function of several variables, and then as we progress through the chapter, we'll be looking at partial derivatives and even eventually multiple integrals. So let's start with a definition and say that a function of two variables is any rule that assigns a unique real number to each ordered pair of real numbers, we'll say x comma y, in a set D, where D is a subset of R2. Since it's ordered pairs, then we're in R2. And it's denoted by f of x comma y. Very much as you would expect. It's just like function notation, but I'm going to have commas inside, and f is just the name of the function. D is called the, any guesses? It's the place from which I can grab my inputs. What is the set of all possible inputs called when you're talking about functions? I'll give you a hint. It starts with a D.
Derivative? Not distance. Distance is a lowercase d. Domain. Oh, that sounds a
D is called the domain. Okay? And then what always goes along with the domain? The range, which is the set of all outputs. R, which would be the set of all z's, such that z is some f of x, y output for every x, y inside D. Just a fancy way of me writing the set of all output, but that's called the range of F. This whole thing is the set of all outputs. Now, because it's just a single number, right, we're just looking at some subset of the reals. Visually, picture it like this. Well, one way to think of it is you've got a set over here in R2. We'll call this D. Right, I'm drawing the rectangular coordinate system to indicate that this is some region in the plane. And every point inside that D, I'm going to assign an output. The output is some number in the real. So this is R2 over here, some R1 over here. So this point, which has coordinates x comma y, goes to some point here. So F maps D into the reals.
R2 to R1?
Yep, it's a mapping, right? So for every point, I mean, think of it like one way. You've got a piece of metal, and every location on there has a temperature. Okay, so every point location has a different temperature.
Okay.
You're just assigning to every point some numerical value. Okay. You could also have on the surface of a map, every point has a height, like an elevation. So at every coordinate, longitude, latitude, there is an elevation, and the elevation is the output of some function. Okay, we'll look at a few examples, but there's 4 ways to describe a function of 2 variables. The first is to do it just verbally. Kind of what I just did to Rick's question. Rick? Kyle. I don't know where that came from. Rickman, that is. Well, I kept going to Alan Rickman last year because it was like a Severus Snape thing, but I have no idea. Sorry, it's early. My apologies, Kyle. 2, you can do it numerically. And I'll give you an example of that in a second. 3, you can do it algebraically, which is our best and favorite way to do it. Algebraically means a formula. And 4, you can do it graphically. And while graphically is nice to be able to see what's going on with the function, it doesn't give us a very good way to work with the function. But we want to be able to switch between these fairly easily, meaning if I give you a formula, you're going to want to give me some numerical outputs. If I give you a graph, you want to be able to see how it relates to the numerical and algebraic outputs of the function. Okay, so let's start with the most common one, which is the formula. Try to keep as much on the screen as I can. Let's say I give you an f of x comma y equals x times the natural log of y squared minus x. So first of all, let's make sure we know what it means to evaluate the function. If I say, what is f of 1 comma 2? You understand what that means, right? What am I going to plug in to get my output.
1 for x and 2 for
1 for x, 2 for y, ordered pairs. So 1 natural log of 4 minus 1, which means I get log 3 as my output. Okay, what about the domain question? What is the domain of f? Remember domains, what you're allowed to plug in. So you look at this function and ask yourself, what restrictions are there on what can be plugged in, right? So, you know, polynomials, nice. I mean, x by itself, you can plug in anything. There's no restriction whatsoever. But as soon as you see denominators, as soon as you see radicals, and as soon as you see things like logarithms, you know there's things you can't plug in. So in this case, for example, what are we not allowed to plug inside of a logarithm? Do you remember? Logs always ask the question of what exponent do I have to raise e2 to get to that number? Right? But I can't get to a negative number by raising e to a power. So you can't have negatives inside of a logarithm. So you have to remember that the log function, you know, when you graph a log, looks like this, and it looks like that because there's nothing on the left-hand side. You can't plug in negatives into a logarithm. So my restriction is y squared minus x has to be strictly greater than 0. So you have to be able to look at this and say, what region on the plane is that true for? What I would do is move this over to this side and look at it like this. X is less than y squared. Now you could go graph x equals y squared to see where it is. You could do it in GeoGebra. You could do it in Wolfram Alpha. You should recognize that it's kind of like a parabola, except the parabola that you're used to is y equals x squared. X equals y squared is a parabola that's laying on its side. So draw a parabola laying on its side. That right there is x equals y squared. You graph it. So then where on this region is x less than y squared? It's less than this curve. X means less than is to the left. So what you end up with is I get to do this in color, but you can just shade this with your pencil. It's everything over here. So visually, that's what the domain looks like. Or I could write it as D is equal to set of all x comma y such that x is less than y squared. That's sufficient to write it out. Now, I know you're not going to be able to write all of this down. You can look this up in the book, but I want to show you an example of number 2 where I give it to you numerically. This is a table that was out of the book. I'm going to just copy this over into the notes. This table right here, can y'all see that fairly well? This is called the wind chill index table. What it does, you know, whenever it's cold outside, you've got a temperature measurement, but you know that whenever the wind is blowing, it actually feels colder than it actually is. So you have the wind chill index, which tells you how cold it feels outside. But that formula is a function of the actual temperature and the wind speed. And instead of having necessarily a formula available, you could be able to look up and find what the wind chill is using a table like this. Now this table is in wind speed in kilometers per hour and temperature in degrees Celsius. But if I were to ask you what's the wind chill when the temperature is, say, negative 15 degrees, and the wind speed is 30 kilometers per hour. Right? You know how to do that. That's just a matter of finding where the row and the column intersect. Right? So you go negative 15 and 30. So the answer's 26. But I could write this as a function I equals, actually we'll do it this way. Let's just say I of t comma w. Index is equal to temperature and wind speed. So if I ask you to find I of negative 15 and 30, that is in fact what we just did by finding that value on the table, which is negative 26. So what you have to have in order to be able to evaluate is, instead of like a t-chart like you would have if it was a function of one variable, you have two variables. You have the t, and for each value of t you have a velocity v. I should have used v, sorry, because I didn't see that v right there. And then this index is the output. But for every pair, ordered pair of t comma v's, you've got an output to that function. Okay. So the most common way for us to visualize is to use a graph. So if I have, for example, let's say f of x comma y equals, I'm going to do square root of 9 minus x squared minus y squared. I think I may have run off and left you. Did I lose track of you? Did I go too fast for you to catch up with the notes? Those that were here whenever I started, I guess I'm worried about. I lost you?
No, I'm good.
You're good? You caught up? Okay. Okay. So what do I mean by visualizing with a graph? Well, real quick, let's write this down. The definition of a graph of a function of two variables, say f of x comma y, is simply a set. It's a set of all points x, y, and z, such that z is equal to the output for all x and y in the domain of f. Okay, so the z is the height of the function. So if you remember from our three-dimensional coordinate system, we labeled this axis x, this axis y. Let's say we have some region down here, which I'm going to call D. I've just drawn a dotted line around a region in the xy plane. So that's like the domain of the function. So we've got a set of points down here that we're allowed to plug in. I mean, that set of points may look like this kind of round oval looking shape. It may look like this shape up here, right? Where you're allowed to plug in points. Now for every point inside here, you're going to have a set of coordinates, x comma y, right? Here's the x, and here's the y. Oh, sorry, that's the x, that's the y for that point. If I plug that point into my function, like I did up here for the index, I get a number out of it. That number is going to represent the height of the surface above here. So we're going to have some thing up here where every point over this domain, there is a point on that surface, so that this distance right here, z, is the output of the function. I mean, that should make perfect sense because it's the exact same idea of when we graph an x and the height of a function, y is the output of a function of one variable. Now we're going to have a whole bunch of points, and we're going to graph all those points up here. That set of points is that surface. Okay? So the graph of a function of two variables is now a surface in space. Right? We did graphs of space curves in the last section where we had one input and multiple outputs, so we were traveling in space. Now we have two inputs, so you take a grid of points or a whole set of points on the plane, and for every single one of those there's a height. So you've got now a surface, okay, that could be all kinds of different shapes. So let's come back to this one right here that I put down before. Now, instead of graphing it by hand, I mean, that's going to just be a bad idea. We've got several tools out there that will help us graph surfaces. I mean, you could do a Google search for graphing 3D surfaces, and you'll find different applets. One of my favorites is one that I've used before in here. It's the GeoGebra. GeoGebra is a software package that's freely available. It's web-based, which means you can go to it from any browser. But they also have apps for your phone and for your tablet devices. You can even go to it on your phone in a browser or on a tablet in Safari or in Chrome and be able to manipulate and draw these graphs. So it makes it a little bit better tool than what Maple is. We've been using Maple for many, many years in Calculus 3, but it costs money for you to be able to have it on your own. This allows you to be able to use some of this kind of stuff at home. It's not as powerful as Maple, but it works fairly well. So I'm going to release your computer back to you, and I want you to open a browser, and I want you to go to our Blackboard class, and I want you to open up GeoGebra. Now what I've done is, instead of taking to the site, there is a GeoGebra site. If you go to geogebra.org, they have actually tutorials on how to use it. They have several different versions of their app. You can do a graphing calculator, which is just 2 dimensions. You can do a computer algebra system. It takes derivatives and integrals for you in much the same way Wolfram Alpha and Maple would do. There's geometry, which, as you can tell from the name, it actually started as a geometry app. It's very good for doing geometry constructions like bisecting angles and using compasses. What we used to do by hand back in high school, you can do using technology. Well, I'm using the 3D grapher to start out with, but I was able to just embed the tool right in Blackboard. And so when you look at the window that's in Blackboard, you've got off to the right-hand side the 3D coordinate system where you can just click with your mouse and drag it around. In the left-hand side of the window, there is an input box. Next to that question mark, if you just click there, you'll see a blinking cursor. Now you can turn the keyboard off. That's for mobile devices, or if you want to use your mouse to click through some different options. But if you click right there, I'm going to type in F-O-R-M-U-L of x comma y equals, I'm going to type square root SQRT. It's going to automatically replace that with the square root symbol. I'm going to do 9 minus x, and then shift 6 for the caret to go up squared. Right arrow to get back down on the baseline, minus y squared. Now, I can roll my mouse a little bit to zoom out. If you just hit enter when you're done, that's the shape you should see. You can toss it around and let it spin. You can look at it from the underneath. You can see that, in fact, this surface is a hemisphere. Now, if you look at the formula, it should be clear to you why this would be half of a sphere. We'll talk about that in just a second. I'll go back to my notes, but I want to make sure everybody has a chance to get in there and get that up and loaded. I see that Darian, Kyle, yours worked. Keyshawn, yours worked. Simone, was yours working? Or, oh, just finally loaded. Yeah, it takes a second the first time it loads. James, yours looks like it's loaded now. So try typing that in. I'll go back and show you what I had typed in. It's f of xy minus, f of xy equals square root. I just typed in SQRT. Although the keyboard lets you use some symbols. I don't know if square root is on there. Yep, that's probably it. By the way, in 3D graphing, you can also plot space curves, which I'll eventually go back and show you how to do. But for now, there's the surface. All right, let's graph another surface. I'm going to jump back and just write real quick in your notes. Let's do graph f of x comma y equals 6 minus 3x minus 2y. So 6 minus 3x minus 2y. So delete. Why isn't it letting me edit? I click the X to delete it. I'm going to type another one. F of x comma y equals 6 minus 3x minus 2y. Is that what I said?
Yes.
Yep. So what kind of shape do you get with that? A plane. Which makes sense that it would be a plane because it's all first powers. It's linear, right? Linear functions graph as flat objects. In this case, it's a flat surface. Okay. I'm going to go back to the notes real quick. Another way that's often helpful to be able to visualize surfaces is something called level curves. Have you ever seen a topographical map? A topographical map is a map of a region that shows you the elevations at each location. And when you think of a certain elevation for a landform, you're going to have this connected curve of kind of a winding path where everything that has the same height is connected by that curve. And then if you move up, you've got another slice. It's kind of like taking the landform and just slicing it off and seeing everything that's at that height, and then slicing off the next height. I've got a picture that I'm going to pull out of the book here and paste in here just for you to see. But it's the same idea as a topographical map. We're doing topographical maps with surfaces. So like this on the right, figure 12, is a topographical map of this lonesome mountain. And you probably can't see very well, but this number right here where my crosshairs are, that says 5,000. And so this dark line here connects all the points of height 5,000. This one over here says 4,500 and connects all the heights of 4,500. Okay? Well, you have the ability to now extrapolate in your mind what the shape of this mountain looks like. You see that I'm going from 4,000 to 4,500 to 5,000 on up to 5,500. What does it mean on a topographical map when you have lines very close together? It's steeper, right? So if you were going to hike up Lonesome Mountain, would you take this path? Or would you take the path where you have the greatest distance between the two? More than likely this, right? Unless you're looking for rock climbing experience, and I don't know what it looks like, but you at least know that it's very steep over here. But you can, just by looking at a two-dimensional picture, see three-dimensional information, okay? So what we're going to do is we're going to practice doing that by taking surfaces and look at their topographical maps, which we're going to call level curves. So the definition of a level curve, I'm going to take over your computers again. Oh, that's not what I wanted to do. There we go. Okay. So let me formally define level curves for you. The level curves of a function f of x, y are the curves with the equations, plural, f of x, y equals k, where k is a number. So what you're doing is you're taking a plane of height k, just flat, parallel to the xy axis, and we're slicing at a given height. So if you look at this one right here, k equals 45, we're going up a height of 45, and we're looking at all the points where that surface has a height of 45. So this light blue line right there is that curve, but I'm just going to graph it in the xy plane. I'm going to graph the curve f of xy equals 45. Since it only has an x and a y, it's just a curve in the plane. And then I'll do it again for k equals 40. I'll graph f of xy equals 40. And then f of xy equals 35, and so on. And so you get this picture down here, and then we throw away the surface and just look at it flat on, and that gives you the topographical map or the level surfaces. That's for k in the range of f. So for example, let's do the level curves of f of x, y equals 6 minus 3x minus 2y for k equals negative 6, 0, 6, and 12. So actually what I'm going to do is I'm going to release your computers again. I'm going to go back to GeoGebra. But this time I'm going to do the 2D graphing. So go back to GeoGebra. Hopefully it won't take as long to load this time, but I'll do GeoGebra 2D graphing. Now I may have just discovered a slight bug in the way that I've presented this to you because it didn't let me put multiple equations in on the surface. And I don't know if it's going to have that same limitation over on this one. What I was going to do is just graph. I take the function, which is 6 minus 3x minus 2y, and set it equal to the first k, which is negative 6. Oh, it did. It gave me multiple input. So that's the first level curve for that function. Do you see what I did? I just took the function and set it equal to the first k. I do the same thing again. 6 minus 3x minus 2y equals 0. Right, just real quick, flashing back. I'm asking us to graph this function's level curves for negative 6, 0, 6, and 12. Which means set this function equal to negative 6 and graph it on the plane. Take 6 minus 3x minus 2y equals to 6. And 6 minus 3x minus 2y equals 12. There are your 4 level curves that I ask you to graph. Which, again, should make sense that your level curves are straight lines for a plane. Because if you just keep slicing up a tilted plane at different heights, okay, they're just going to be straight lines. Okay? Now, level curves should not touch each other, or at least they shouldn't intersect at angles. That would be something is definitely wrong. They can get really, really close to each other. If they touch, that means you're doing a straight jump from one point to the next. You're going straight up and over, okay? Which would mean you have a discontinuous function. And we're going to spend the next couple of sections talking about limits and continuity, so we'll save that for then. But for now, these should not cross each other. That can't make sense with level curves. All right, let's do, just for practice, let's do level curves. For our other function we did, f of xy is the square root of 9 minus x squared minus y squared. We'll use k equals 0, 1, 2, and 3. So I'm going to go back in here and I'm just going to delete these by clicking the X. Or right click and click delete if I can't get to the X. I'm going to make my life a little bit easier this time. Instead of having to type the square root of 9 minus x squared minus 9 squared every time, if I declare my function I should be able to just reuse that in my formula. Nope, it didn't like that. I'm going to delete that. Let me try one more thing. I meant to do colon equals square root of x. No, sorry. 9 minus x squared minus y squared. We'll try that. If that doesn't work, then we may just have to type it every time. Oops. F of x comma y equals 0. Nope, doesn't like it. All right, let's just start over. I'm going to do square root of 9 minus x squared minus y. Dang it. I can't type. Keep messing up. Square root 9 minus x squared minus y squared equals 0. What did I just do? That should be something. I don't know what's wrong. X squared minus y.
That was the way.
No. I don't know why 0 isn't working. Well, let's keep going. Square root of 9 minus x squared minus y squared equals 2. Square root of 9 minus x squared minus y squared equals 3. All right, so what I should be getting with the 0 one is a circle of radius 3, but I don't know why I'm not getting that. I'll have to do some checking to see what's going on with GeoGebra. But we got 2 of them on there. By the way, if I do square root of 9 minus x squared minus y squared equals 3, that's actually a point 0, 0. That's the only one that satisfies that. You can see that by looking at the graph, or sorry, at the formula. If I did square root of 9 minus x squared minus y squared equals 3, square both sides, you get 9 minus x squared minus y squared equals 9. The 9's cancel, you move those to the other side, x squared plus y squared equals 0. And the only way for that to happen is 0, 0. So this one right here is just a point. This one right here should be a circle of radius 3. If you do those level curves. Okay, so the last thing I want to do in my last 2 or 3 minutes of class here is jump dimensions. We can have functions of 3 variables. F of x comma y comma z. We can have functions of n variables. F of x1, y1, x2, y. We'll call it f of x1, x2, x3, xn. You can have any number of variables and have a formula that outputs a single number based on those 3 different inputs. And there's actually a lot of different ways for us to apply that in the real world. You may think you're limited to only having 3 points because, or three coordinates because you're in space. You have x, y, and z. But you don't always have to think in terms of spatial dimensions. You can think in terms of all kinds of measurable quantities that have an impact on something. For example, your grade in this class is a function of dozens of variables. Because how many different inputs does your grade, your final average for this class, depend on? Homework set 1, homework set 2, homework set 3, homework set 4. You got 20-something homework assignments. Exam 1, exam 2, exam 3, right? You've got your final exam. So you've got at least 24, 25 variables that you can move any one of those and it has an overall impact on your grade, okay? What variables impact the temperature outside today? Wind is one, or how it feels outside is, wind is one of them. Barometric pressure, you've got humidity. There's all kinds of climate variables that will affect any given temperature of the day. So you think in terms of not necessarily spatial variables, but any kind of input into a function that gives you a numerical output. The problem with both of these is graphs are then very challenging. Right? To graph a function of 3 variables would require 4 dimensions. Right? Because you get W as the output for every X, Y, Z input. So you'd have to be able to graph a point X, comma, Y, comma, Z, comma, W to be able to visualize it. So we're really out of luck being able to visualize these things, although we can use what are called level surfaces instead of level curves, where we would set f of x comma y z equal to k for k in the range of f. So instead of connecting points on the plane of fixed height, you're going to connect points in the space of like output. I'll bring some pictures back on Monday to show you what some of these level surfaces might look like. But that's really all I wanted to cover out of this section. So we'll come back and do some more work with functions of 2 variables for the most of this chapter and look at some surfaces. But you have what you need to be able to work the problems of this section. And use that GeoGebra applet that's right there in Blackboard for your homework to be able to graph the surfaces that are in there. Should be real easy and quick. They're all multiple choice, so you just have to plug it in and find the one that looks like what the graph on the screen looks like. Okay? Should be easy. All right, that's it. So I'm going to stop there.